Good day, everyone. We are here to discuss with you certain topics, which includes electroluminescence, localization techniques, and photoemission microscopy. First, let's proceed with electroluminescence localization techniques. For the ILO, for this discussion, we will be able to define electroluminescence and its processes and how it occurs. The concept on how the PEM detects defects, equipment and the application used in PEM, and we will be able as well to recognize the different classification of emission sources. First, before we initially define electroluminescence, let's see first where it is being used and how and why. To proceed with that, the first question to answer is what is fault localization? It is a manufacturing step that attempts to isolate the defective areas on the die of failed units. For this, there are two main categories of fault localization. First is the active, and the second one is passive. For passive or for active localization technique, it is typically used as a scanning ionizing beam or laser beam to stimulate the failure sources or the failure source. While for the passive technique, it is most common type in photon emission microscopy, which will be discussed earlier or later on rather, by means of sensitive cameras. It relies on the fact that various types of failure will emit small amounts of light and when the failure is occurring. So what is electroluminescence? It is actually the characteristic of material, typically a semiconductor, that enables it to emit light in response to an electrical current or a strong electrical field. So basically, electroluminescence is a process of emission of light to simply detect um, the specific defects on a semiconductor material. So there are so basically electroluminescence is about emission of light or producing light. And there are two ways to produce light, which first is the incandescence, where electric current is passed through a conductor whose resistance to the passage of current produces heat. The greater the heat of the filament, the more light it produces. While on the other hand, the luminescence, in contrast, is the name given to all forms of visible radiant energy due to causes other than temperature. So basically, there are what do you call it, light emission, not only because of temperature, but on more of more than one factors other than temperature. And there are types of luminescence, which includes photoluminescence, which is common in glow in the dark objects, which we usually see in toys or even in other simple devices or material. With light that is produced after exposing a photoluminescent material to intense light. Second one is the chemiluminescence. Is the name given to light that is produced as a result of chemical reactions such as those that occur in body of a firefly. Cathodoluminescence, on the other hand, is the light given off by material being bombarded by electrons, as in the phosphorus and the faceplate of cathode ray tube. So this is the example of cathodoluminescence. And of course, electroluminescence as well is a type of luminescence, wherein it is the production of visible light by a substance exposed to an electric field without thermal energy generation. So by the help of electric field or electric current, electroluminescence happens or being produced. Let's talk about more electroluminescence. Current we're in this process, current is fed into a solar cell, essentially a large diode, and radiative recombination, or the radiative recombination meaning refers to the band-to-band transition of an electron on a specific conduction of a semiconductor, which causes light emission. It is as an indirect band gap semiconductor. Most of their combination in silicon occurs via defects. And also, electroluminescence provides a wealth of data about the related uniformity of solar cells and modules. It is non-destructive and relatively fast with measurement times of 1 second possible. So electroluminescence process is a type of fault analysis technique, or basically this is a fault analysis technique which is a non-destructive and provides more data, or let's say faster and reliable data when it comes to detection of defects in a certain semiconductor device. Factors that can, in many cases, negatively affect device power and lifespan but are invisible to human eyes. So basically, these are some factors or defects na nakaka-affect sa lifespan ng isang electronic device or ng semiconductor. Um, One is microfissures and chips, as well as complete breakage in one or over several cells. Device impurities, wafer crystallization defects, or yung defects among fabrication ng ICs on a substrate. It also includes interrupted contact fingers and or cell breaks that result in electric separation and therefore deactivate individual cell pieces. So ito yung mga, let's say, naputol na connection due to um contaction ng, or with due to contact ng kamay, because some of the semiconductor materials, for example yung mga microprocessor or yung CPU of the computer, we are not allowed to what do you call it, to hold or even touch it um on a bare hands, specifically yung gold chip or yung gold part, because it really affects the electric conduction of that semiconductor device or material. General signs of defective cell processing. So as I have mentioned earlier, these issues and defects, or these are all issues and defects, which can be detected with electroluminescence imaging in just a few minutes, and allow one, or let's say, which allow analysts to draw conclusions about the tested modules of materials and processing quality. So again, electroluminescence is a way of detecting defects which is invisible to the naked eye due to the process of light emission through electric field or large electric field or electric current. So this is the example of electroluminescence of a monocrystalline silicon wafer, wherein on the image we can see the, what do you call it, device impurity showing on contact probes, also a print problem or showing microcracks. The intensity of the light given off is proportional to the voltage, so poorly contacted and inactive regions show up as dark areas. So meaning those black areas are not contacted, what do you call it, are not contacted with enough voltage and current. But the thing here is to focus on the part which needs to be tested or looked into. The microcrack and printing problem are not detectable with visual inspection. So again, since hindi siya visible to the naked eye, electroluminescence process was done. For the summary, electroluminescence again is a characteristic of a material, or basically semiconductor, that enables it to emit light in response to an electric current or a strong electrical field. And also in electroluminescence, current is fed into a solar cell, essentially a large diode, and a radiative recombination of carriers causes light emission. Now we're going to proceed with photon emission microscopy, which will be discussed by Mr. Malayba.
So, good day everyone, and I am about to discuss about the photon emission microscopy. So, for the first one, what is photon emission microscopy? And it is a global failure site, which is it is most the dominant technique widely used in IC failure analysis, and it is also simple, quick, and at the same time non-destructive. At because ginagamit niya yung pagka non-destructive niya, ginagamit niya lang yung pagde-detect ng illumination ng naki-create ng IC devices natin. So hindi natin sinisira mismo IC device natin. So it is often the primary tool for localizing many types of common defects such as gate oxide shorts, degraded PN junction, and for identifying MOS transistors in saturation due to interconnection short or open circuits. And for the next one is uh, photon generation results from energetic hot carrier production and subsequently energy release in both silicon and GAAS devices. Emitted photons have energies in the near IR and visible wavelengths. These hot carriers are produced by various mechanisms and defects that cause local high electric fields, such as transistor saturation, oxide leakage, and junction leakage are common hot carrier mechanisms. So yung mga hot carriers natin, yan yung mga dinedetect ng PEM natin or photon emission microscopy na kayang i-detect ng device natin or ng technique na 'to. So, paano naman na-create yung mga hot carriers na yan? Ganito siya, photon emission and absorption. Every time na yung transition ng electron natin from lower energy to high energy or vice versa or higher energy to lower energy, nagkakaroon tayo ng photon emission or photon absorb. So, every time na kunyari, ang isang transistor natin is naka-off siya. Tapos, so dapat wala tayong madedetect na kahit anong photon emission dun or photon absorb. Kapag may defect yung ang transistor natin inside the device or the IC natin, magka-create siya ng illuminance ng photon emission na madedetect ng PEM natin. So, ang isang example nito is yung next one. Ayan. So as we can see from the example, yung isang typical transistor natin which comprises of source, drain, and gate. As we can see, yung gate natin banda is nag-illuminate siya, meaning meron tayong gumagalaw na electron. So, anong meaning nun? So, yung electron natin, kung pag gumagalaw siya, magkikreate tayo ng photon emission na nadetect ng PEM natin. And yung itong example na to is yung transistor natin na 'to is naka-saturation mode siya. So, even though na hindi siya nagka-conduct ng electricity or something naka-off na yung transistor natin, meron siyang naka-saturation mode yung transistor natin which is a defect pa rin. So, next one natin is equipment and application. So, the first one is the PEM setup. So, yung image na nakikita natin dito is yung setup ng microscope natin. Typical na setup to ng lahat ng microscope pero sa PEM ganito pa rin. So, yung light source natin, um, um, bago natin i-further PM, punta tayo sa PM setup, paano muna gumagana yung microscope? So, yung microscope natin is gumagana through light source, and yung light source natin, tatamaan yung pinaka-object na gusto nating tignan. Then, lahat ng ilaw na na-absorb and na re-reflect ng image na yon, ibabato niya pabalik pataas, papunta sa optical microscope and optical filters, and at the same time, doon na pupunta sa image intensifier and video. So, ganun gumagana yung microscope natin. Ganun din naman gumagana yung PEM. Same concept lang din sila. So PM tool is usually based on a wafer prober with the product or structure under investigation being driven via electrical probes or probe cards or locally open IC position on the stage. The faint light must be detected very sensitively, usually with a cooled CCD or charge coupled devices, or especially for dynamic measurements and more sophisticated detectors. For localization, the resulting PM image needs to be overlaid with a micrograph of the structure, which requires some image processing. And next one, which is the optical path. The microscope, only an adjustment tool on a prober, has a crucial function in PEM. For an image of the light reflected from the IC surface, the lamp is bright enough. But the faint photoemission signals need the microscope as optical path to get transmitted to the detector. So yung kailangan yung optical path niya walang obstruction, at the same time dapat yung light source natin hindi ganun kalakas, kasi kung mas magiging malakas yung light source natin compared sa ide-detect natin, which is yung photon emission, mas kumbaga hindi natin makikita yun, kundi hindi natin made-detect yung pinaka ano natin, pinaka objective natin using the PEM technique. So any loss of intensity should be avoided, and most important is a high numerical aperture or NA of the objective with high working distance and necessary for manipulation still maintained. So yung NA natin yan, commonly known yan, sa ginagamit yan sa mga cellphones natin or specs siya ng camera natin. So yung NA na yan normally siya yung the higher the better yung number niyan, your figures. The higher the number, ibig sabihin nun, mas malaki yung amount ng light na makaka-capture ng isang camera. Yun yung meaning ng a high numerical aperture. So the third one is the detectors. And the ideal detector is sensitive in the spectral range from 1500 down to 500 nanometers wavelength. Images the lateral resolution of microscope has gigahertz frequency range and with stroboscopic gating option and operates at TV image frequency. And in the past, image have been standard, but today's PEMs are usually equipped with silicon CCDs. Some have CCDs of compound semiconductors. So ano yung naman yung silicon CCDs? Yung silicon CCDs, sila yung charge coupled devices na tumatanggap ng light, which is um, tinatanggap niya yung light tapos generate niya yung light na yun, generate charge that can be read by electronics and turn into digital copy of light patterns falling on the device. So yun yung purpose ng CCDs. And the next one is the backside inspection. So multi-level metallization, packaging innovation, or flip chip technology are obstacles for PM and other localization techniques. And even direct probing from the top of the chip, silicon can be transparent above 100 nanometers spectral range due to its band gap. This spectral part of photoemission is accessible also from the backside of the chip, which makes PEM one of the natural techniques in the backside approach. So yung multi-level metallization natin, yan yung mga protection na nilalagay or additives sa packaging natin para for further protection ng device natin and packaging innovation. At lahat ng to, yung unang nabanggit is parang hindi naman siya pangit, kumbaga parang hindrance lang siya sa na kailangan ma-overcome ng PM technique natin. So, other technique na ginagamit is yung backside approach natin, which is yung PM natin is dinedetect niya from the bottom, hindi siya from the top. So, yung the next one. Ayan. Ito yung here's some of the challenges of backside inspection. So, silicon CCD detector does not pick backside detection because its function is based on live absorption and in silicon, which is the complementary effect of to transparency. So, yung pinaka-objective ng PEM is yung i-absorb yung light natin while the silicon is effect to transparency, which means 'pag transparent, pumapasok lang or tumatagos lang yung ilaw or nagre-refract. So silicon has a diffraction index of 3.4, which is a dispersion is a problem then which makes blurs images, and because of this the optical path is focused only for a smart part of the spectrum. And the last challenge for backside inspection is heavy doping of the substance reduces transmission even above 1,100 nanometers seriously due to band gap narrowing and absorption of free carriers. And in this case, the small spectral effectivity of silicon CCD for backside in investigation is even further reduced. So the more heavily doped yung isang package natin or device natin, mas nababawasan yung effectivity ng silicon CCD natin, which makes a lot difficult to read for our PEM technique. And the last one would be the heat radiation. Heat radiation emits in the regularly detected spectral range only at temperatures significantly higher than specified for ICs. Rarely, metallization shorts may reach this temperature range for a short time and produce an emission spot, but evidence should be verified in this case. So, meaning yung metallization shorts natin, nag-i-emit din sila ng photon emissions, and at the same time, yung 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 taas ng temperature dito hindi natin bina-vary dahil nga microscopy lang na yung ginagamit natin. Then kapag nangyari 'tong metallization shorts, mas ma-further natin na ma-recognize yung pinaka defect natin kapag ginamit na natin yung thermography technique, which is more focused on radiation infrared and temperature sensing. And for summary, for the conclusion, the concept behind the PEM is that every movement of the electron from the high energy level to low energy level and vice versa, there will always be a photon absorption or photon emission that a PEM can detect, and this movement signifies an irregularities happening inside our ICs. Definitely if naka-turn off yung ICs natin. And equipment and applications on using PEM are as follows: PEM setup, optical path detectors using the silicon CCD or charge coupled devices, backside inspection, and at the same time, heat radiation. Thank you.
Good day. I am here to discuss the classification of emission sources. First one is light emission generated by scattering of field, field accelerated carriers, or FEE. Um, most photon emission spots in microelectronic failure analysis are electrical field induced. Um, this includes most transistors in saturation and most leakage currents in silicon. Even ohmic leakage currents as they occur, for example at gate oxide or GOX, defects can be detected if the current density is locally high enough to create FEE. GOX defects usually need a local voltage drop of 2 volts or higher for PEM detection. Fowler-Nordheim currents create FPE due to scattering in silicon or polysilicon, respectively. Effective field variations of the GOX area resulting from lateral polysilicon resistance or local GOX thinning are accompanied by FN current variations that can be recorded by PEM. Next. Next is the photoemission generated by radiant electron hole recombination, or RPE. RPE is subject to IC failure analysis mainly for latch-up investigations or yung mga short circuit sa sa integrated circuit natin. Forward bias effects occur here and there if wells are floating. It is very important for fast bipolar circuits and power devices in their switching properties. Kung makikita natin, nasa FPE yung space charge region natin. Nandito yung reverse bias junction, silicon leakage currents, MOS transistors in saturated mode, ESD protection breakdown, and yung bipolar transistors in active mode. Nasa FPE din yung locally high current tsaka yung Fowler-Nordheim current. Andito yung GOX defects, leakage, and GOX leakage sa current. Nasa RPE naman natin yung EH recombination or yung electron hole recombination. Andito yung forward bias junction, yung bipolar transistors in saturated mode, and tsaka yung latch up. Next. Leakage currents across a PN junction in silicon. A good reverse biased PN junction is only carrying enough current to show up in FPE when in avalanche mode. A leaky diode is emitting light above detection limit at considerably lower voltages. Except yung mga well substrate diodes, if a current is leaking all over their large area, yung current density pwedeng di ma-reach ng detection limit. Leakage currents in silicon are the classic PEM application for failure localization. They produce emission spots when passing through or created in an SCR FPE. Spiking is one more kind of junction leakage. Highly localized junctions or capacitors allow detection even in picoampere range. Next. Saturated MOSFETs or hot electrons. The current through the inversion channel of a MOS transistor in ohmic state is low resistive and usually not accompanied by light emission. Only after pinch off in saturation, it passes an SCR from pinch off point to drain. The light emission is proportional to the back bias or substrate current. This means the PEM signal is too low to be detected in logical states, low or high in digital circuits. Dito sa kapag nasa static operation mode, dapat walang photon emission na mag-occur kapag sinabing good digital yung IC natin. Kapag each PM signal is indicator of a fail. Ibig sabihin kapag nasa static operation siya, kapag merong PM signal, pwede itong mag-indicate na merong failure. Pwedeng magkaroon ng floating gate or leaky gate, tsaka leakage junction or avalanche. Kapag naman nasa dynamic operation, pwedeng makadetect ng photons as indicators of correct function. Whenever FETs switch, they pass the maximum substrate current condition and emit light. Dynamic measurement in picosecond resolution of photon emission can be used to track signal propagation and timing of the circuitry for design verification. Next. Next is the Fowler-Nordheim or FN current. Leakage currents of intact gate oxides consist of tunneling phase and a path in which the carriers get accelerated by the electrical field. The emission mechanism is again FPE, but the spectral distribution is very different from the other sources. The emission intensity is almost equally distributed over the recorded spectral region with a relative maximum at 1.8 electron volt. Next. Um, Next is the locally high currents or tin oxide breakdown. Um, GOX defects belong to the most important failures which get localized by PEM. But the breakdown of tin oxides does not necessarily produce an SCR, especially when poly and well are duped of the same type. The explanation is the current density is high enough to create a voltage drop at the fail site, which in turn implies FPE in PM spectral range, typically greater than 2 volts. This makes GOX breakdown usually observable in PM, uh, and it also explains why not every breakdown can be found in PM. Some emission spots are unstable or vanish after a while, uh, or locally high current melts breakdown region. It enlarges broken area and reduces current density. And some fails even heal electrically during operation. Next. Next is the bipolar diode. Here the focus is on the characteristic emission images from diodes in ICs or related test structures. The figure shows a diode test structure with two band pads above and below, and two metal one interconnect sheets covering most of the device itself, which appears only as dark line in between. Makikita natin dito na at forward bias, the interconnects are blocking most of the light emission underneath, and only on the left and right edges, the RPE emission is reaching the detector. Furthermore, the recombination of the carriers diffused away from the diode area is clearly visible. The diffusion length can be easily calculated from this emission image. And a typical sign of RPE is the widespread of the signal due to carrier diffusion. Uh, and then sa reverse bias, in the reverse bias case, the image looks completely different. At the edges of the device, sharply localized FPE spots are visible in avalanche condition. This reflects the fact that the highest field strength occurs at corners and edges of the devices. If detectors allow real-time mode, these light spots fluctuate strongly in intensity and location. Next. Next. Next is the bipolar transistor. For the bipolar transistor, operation shows in the figure has been chosen for better observability. A MOS transistor or driven in its parasitic bipolar mode, with the well under the gate acting as base. This way, the structure is laterally orientated, whereas regular integrated bipolar transistors are vertically structured, and the explained effect, not that obvious. A bipolar transistor in active mode operates the emitter basis junction forward bias and the basis collector junction reverse bias. In saturated mode, both junctions are forward biased. Uh, the emission images show a very sharply localized signal like FPE in active and a broader signal like RPE in saturated mode. The reason is in active mode, the reverse bias base collector diode produces a much steeper diffusion slope in the base and concentrates the current into the collector direction. Next, um, next is latch up. Latch up is a parasitic bipolar effect of two wells and their diffusion, which define a four-layer device like a thyristor. During lash up, the thyristor turns on in forward direction by strong minority carrier injection of the diffusions, which floods the wells and the junction of the two wells. Turn-on condition is a combined amplification factor greater than 1 of the two-folded bipolar parasitic transistor. They may be reached by a parasitic-based current, where the minority carrier diffusion from the protection diode serves as additional injection or base current in the latching system and is turning it on. In other cases, a breakover condition may be reached by field peaks combined with a tight design and avalanche produces latch up. Uh, the emission signal of a stable latch up is always RPE because of the high excess carrier density of electrons and holes. At the turn-on moment, in the breakover case, FPE occurs due to avalanche multiplication. Next is the emission spectra. There are three basic types of spectra. The first one is the recombination radiation or RPE with a steep slope due to low electron temperature representing only heat, especially obvious in the latch up case. Latch up hits the device significantly, even the slope shows. The next is the radiant scattering of field accelerated carriers, or FPE, with the carrier still approximated to obey Boltzmann statistics. So the exponential slopes represent the kinetic energy with electron temperatures of 1500 Kelvin and more. The next is radiant scattering of field accelerated carriers FPE of Fn currents through intact tin oxides with and therefore not showing a significant shape in the spectra, except for the relative peak at 1.8 electron volts. Uh, for the summary, successful failure localization with PEM requires light emission spots generated in silicon. The key issue is a locally concentrated high current density that creates first a local electric field to accelerate a sufficient number of carriers for scattering accompanied by light emission in the PEM sensitive range or the GOX breakdown. Second is enough carriers in a space charge region to certify a sufficient number of radiant scattering events. Or the next one, enough carriers to diffuse as minority carriers in the forward bias case to certify a sufficient number of radiant recombination events. The failure analyst should always try and understand a possible and probable reason in the circuit that can cause the detected emission phenomenon before further preparation because these processes are final. In general, the emission spot is not always identical to the failure location. A flip-flop may not switch correctly and the result can be a gate of another FET in intermediate state which may emit light and so on. The key is to always verify the reason for the light emission in terms of device and circuitry operation. Often there is more than one reasonable explanation, and the analysis job is not done before they all have been investigated.